and keep slowing down. At some point, in theory, they're gonna stop moving at all, completely. There's no kinetic energy whatsoever. At the point when there's no kinetic energy, that is what is defined as 0 Kelvin. 0 K, notice absolute zero. The temperature at which movement stops. Movement of atoms stops. And there are some physicists who are trying to get as close to that as possible, but I think the current record for the coldest atom is on the order of picokelvin, 10 to the negative 12th Kelvin. And sometimes I'm asked why they do it. I think primarily for bragging rights.
Do you know what 0 K is equal to in Fahrenheit?
Not off the top of my head. It's negative 473. I don't know if that's right or not, but it's in that ballpark, I think.
400?
Negative 400 something,
No.
I think. All right. Now, degrees Celsius, something people are more familiar with. Occasionally I might refer to it as centigrade, just because of when I was born, and it was at one point called centigrade, because you go from 0 to 100, so there's 100 grades there between freezing and boiling point of water, thus centa meaning 100 grades. So if I take the temperature in degrees Celsius, and let's make sure I do this the right way. So I take the temperature in Kelvin and add 273.15, I get degrees Celsius. Sorry, subtract. That's a big difference there. Try that one again. Degrees Celsius plus 273.15 gives me Kelvin. So 0 Kelvin is the equivalent of negative 273.15 degrees Celsius. And then we have Fahrenheit. Oh, well, degrees Celsius was defined based upon freezing point of water. At 0 degrees Celsius and boiling water. 100 degrees Celsius. And the advantage of that is if you're coming up with your own system, it'd be nice if you could come up with something that people throughout the globe could be able to do. So if you take pure water, find or close to pure as you can get, distilled water, freeze it, you now have you know what 0 is, boil it, you know what 100 is, and you can now do comparison of measurements throughout the world. Or probably at the time, as far as they were concerned, throughout Europe. But we have our system, Fahrenheit. What's the freezing point in Fahrenheit? Degrees Fahrenheit.
32.
Say it again.
32.
So that's 32 degrees Fahrenheit. What's our boiling point?
212.
How on earth did they come up with that? 32 and 212, why? Well, Fahrenheit was trying to figure out some system, and he thought, well, everyone's body temperature is roughly the same. Why don't we make that 96? So he established his body temperature at 96. It's not that anymore, but at 96. And he sets 0 at the coldest thing he could make. So presumably there's a recipe somewhere for the coolest thing that Fahrenheit could make. So he set 0 at that, and then boiling and freezing come out of that. Why 96 though? What's special about the number 96? Hint, they didn't have calculators, or the calculators at that point were people. Similar to why Babylonians used 60 as their base system. Yeah, 96 has a lot of things that can go into it. It's easily divisible by a large number of things. It makes the math easier. Now, I don't know if it was particularly cold that day or why body temperature is now considered 98.6. Actually, what is the average body temperature now? What's normal? 98.6 came from a survey that was done in the mid-1800s. That is not the average body temperature today. What is the average body temperature today?
When I checked my residence temperature, a lot of it was like 97.3 or 2. 97.
That 97.9 is the average, human average now. And some people can be below that, and some people will be above that. But 98.6 is still considered body temperature, although that you're probably running a very low grade fever. Okay, and so you can convert degrees Celsius into Fahrenheit, or Fahrenheit to degrees Celsius, and then get Kelvin. As a quick and dirty, if you want to go from degrees Celsius to Fahrenheit, double it, add 30. That gets you a ballpark. So 20 degrees Celsius, double it, add 30, puts you about 70 degrees Fahrenheit. And it works for the temperatures that we normally deal with. All right, so Kelvin. So the units of specific heat, well, if I just isolate that, it's going to be a joule per kilogram Kelvin. So if I went into online and I typed in specific heat of aluminum, I'm not necessarily going to get those units. Why? Because, again, thermodynamics people were doing their own stuff. They have lots of tables based on other systems, and they said, you know what, that's whatever, but we're not going to change. So another unit of energy that is often used here, instead of joules, it's the calorie. Lowercase c. Instead of kilograms, they'll often use grams. And you might still see Kelvin or degrees Celsius, but calories per gram degree Celsius is also a common unit that you will see. So what is the relationship between that calorie right there and food calories?
They're not the same.
They are not the same, but there is a relationship between them.
I learned about this in middle school, but I forget.
Okay. Anyone with nutrition background? Or middle school background apparently? I don't know why they decided to do this, but my speculation is they didn't want to deal with the large numbers. 1,000 calories is equal to 1 food calorie. Or, as abbreviated, 1 exceed calorie. Or 1 kilocalorie. So when we talk about calories in here, I will specify food calorie. Otherwise, try that again. If we're talking about calories in here, we're most likely going to be dealing with the physics calories, these right here, and if I'm dealing with those, I would specify food calorie. That's a 1, not a 0.1. All right, questions up to here?
Sorry.
All right, so I have a substance. I have a 4 centimeter by 3 centimeter by 5 centimeter block with a mass, with a density of, let's make it 3.5 grams per cubic centimeter. I put 700 calories of energy into it. And the block goes from 5 degrees Celsius to 47 degrees Celsius. What is the specific heat of the block? Specific heat. Now, I am making the assumption that this block is not changing phase. It's not melting or boiling or any. None of that is happening, so it stays in whatever, presumably solid form. If it's not solid form, I'm not quite sure I can really call it a block. All right, let's take it piece by piece. I have one formula so far. I know that the energy put in is equal to mc delta T. That should be a capital T there for temperature. That is what I'm trying to find. So I need to figure out Q, M, and delta T to start with. So first off, Q. What is Q?
700 calories?
Yes. So 700 calories. What is delta T?
42.
Give me the whole thing.
32 degrees Celsius.
There we go. And the mass. How do you find the mass? I didn't give it to you explicitly. What information have I not used yet?
The density.
And,
The numbers up there, 435.
okay. So it comes down to what is density? All right, so density. The symbol that I use for density is a rho. I don't know what they use in chemistry. they might use the letter D. It's crazy. What is density?
It's like how thick, how much stuff is inside of something?
Okay, that's part of it. So how much stuff, we generally call that mass.
Yeah.
And what's the other piece of it?
And like how much there is in one certain thing?
And how what?
Like how densely packed it is in one thing?
I hesitate to use the word dense when defining density. Density is a measure of how dense it is. I mean, that. All right, so how much stuff it is, and what's the other piece of it? Without using the word dense?
How tightly packed together it is.
Okay,
How much mass is it?
so what you say?
How much mass?
Okay, how much mass, and there's another piece of it.
How much volume?
That's it. So it's how much mass and how much volume it's crammed into. So density is just mass over volume. Hewitt makes a reference at one point to weight density. Hewitt's book is the only book I know of that ever made reference to weight density. So density is mass divided by volume. All right, I'm trying to find the mass. I need my mass in my equation here. So I know mass, so the density I give you, 3.5 grams over cubic centimeters, or cc's. And volume?
4 times 3 times 5.
Yeah, it's a block, just length times math times width. So 4 times 3 times 5 is
60.
60, all right. So that's equal to the mass divided by 60 cubic centimeters, because it's centimeters times centimeters times centimeters. So the math problem that we're dealing with here is 3.5 is equal to m over 60. That's the math problem. What is m?
The mass.
210.
Yeah, look for a number.
210.
210? So mass 210, what are the units?
Grams.
Yeah, grams. Because the density, that's grams there, times C. So now we need to solve for the specific heat, so it doesn't matter which one I divide by, so let's divide by 210 first. 210. So I end up with whatever 70/21 is, equals 42C, then divide by 42. And so my specific heat is 700 divided by 210 divided by 42. Okay.
0.079.
0. What'd you say again?
0.079.
0.079. What units? Think about what I divided in order to get to the 0.079.
You divide it by grams and then you divide it by Celsius.
And what did I divide by those?
Calories.
So I got a calorie over gram degrees Celsius. This is not a completely out of the ballpark number. I want to do one last thing if I wanted, so I said the temperature went from 5 degrees Celsius to 47 degrees Celsius. In Kelvin, I would add 273 to each of them. So it goes from 278.15 Kelvin to 273. 273.5, so it becomes 320.15 Kelvin. So if I'd done it in Kelvin, I would have had that. What's the change in temperature in Kelvin? No.
Saying 42.
So when you're dealing with change in temperature, Kelvin, degrees Celsius are the same when dealing with change. And so this answer here could just as equally be 0.079 calories per gram Kelvin.
Okay.
Do recognize that if you are saying, using Kelvin, it's just Kelvin, it's not degrees Kelvin. If you're doing Celsius or Fahrenheit, it is degrees Fahrenheit, degrees Celsius officially. And then the last bit, one little bit of trivia. In the international standard, Kelvin is baseline, it's based upon degrees Celsius. We have degrees Fahrenheit. What is that? What units are used for absolute zero in our system? So for degrees Celsius, it's Kelvin. For degrees Fahrenheit, it is. Looks like you're about to say it.
I had it, but I lost it. I know it. It's
I feel bad for the guy because he gets a unit named after him and no one ever uses it. Rankine. Rankine's the guy. R-A-N-K-I-N-E.